Today, we're going to be going through the Learning Networking Fundamentals path on TryHackMe. And we're actually going to start with the What is Networking room in this video. And that's going to help us understand kind of the basics of networking, some of the methodologies, and just kind of the broad scope, big picture details about networking. So whenever we start to dive into some of the other topics, especially whenever it comes to cybersecurity, it's all making sense. And we're going to get started on all of that right now. So here you can see the networking fundamentals path is the second path that you'll have to do. And if you haven't already seen the cybersecurity introduction room, we completed that already. So definitely check out the channel if that is something that you are interested in. But now we're going to be diving into the network fundamentals path. And specifically in this video, we're going to be going through what is networking. And this will give us the fundamental picture on what networking is. So what is networking? Well, it can be found in all walks of life, as they say. The public transportation system, how is it that buses are being tracked by your central command and control node that allows them to be able to track, okay, this bus is on time, this bus is late, this one's ahead of schedule, these drivers are going to be off their shift here in a minute, these ones are coming on a shift, how we get these buses in. It's a giant puzzle, and it all requires networking. Infrastructure such as the national power grid for electricity. Absolutely. Again, and a lot of this kind of stuff, it requires, some sort of command and control. And in order for you to be able to, command and control, you have to have networking with your endpoints. Meeting and greeting your neighbors, pretty basic. And a lot of this is a bit more theoretical. You might even, if you want to say hey to them online, that requires networking. Then postal system for sending letters and parcels. If you have, some method of tracking that online, then it requires some amount of networking from the different facilities that your parcel is passing through. But, and I think it's talking here just about the idea of networking, but, there's actual networks, computer networks involved in these as well. So it can literally be formed anywhere from 2 devices to billions. And by billions, we're talking about the wider internet. The internet is a network. It's a giant, that's why we call it the net, right? The internet, it's the network. These devices include everything from your laptop, phone, to security cameras, traffic lights. And if you go to Shodan, you can actually see some of these devices that are publicly broadcasted or accessible to the internet. It's kind of freaky. So definitely be careful if you have, security cameras. A kind of a famous and frightening example is a baby cam. Sometimes people don't change the default passwords on their baby cam, and then they don't realize that their baby cam is accessible to the internet. And people find that. So that's very scary. I mean, obviously change the default password, but do try to make sure that it is, not exposed to the internet. You'll have to edit that in your router. So we'll take this diagram and let me go ahead and reset my progress here before we dive in. Spoiler alert. So what's a key term for devices that are connected together? Networking. Beautiful. What is the internet? So we've established kind of what a network is, but the internet is basically the giant network, right? And you're combining different, smaller networks. You can, think of those as a subnet, but smaller networks that let's say an organization has, and then your small home network, and it's networking all of those together so you can all access, different resources. It allows you to basically go to Facebook, or it allows you to VPN for work, stuff like that. So, we have all this text here. I know a lot of you guys were kind of saying, hey, just summarize the text. Basically, that's what we're talking about. We're going through the history of the internet right now. And the first iteration of the internet was the Arpanet in the 1960s with the DoD, the U.S. Department of Defense. But again, it took a little bit longer for it to be an actual internet that we know today, the internet that we know today, invented by Tim Berners-Lee, and that was the creation of the World Wide Web. Here you kind of see what I was mentioning earlier, where you have these different networks that are all networked together in the internet. That's really what the internet is. It's just the giant network that networks other networks. How many times can we say networks on this stream? Not enough. So who invented the internet? Tim Berners-Lee. I spelled it right. So good. Terrible. Unacceptable. Identifying devices on the internet. And I'll view this site here in just a second. To communicate and maintain order, devices must both identify and be identifiable on the network. And so you probably already know about these IP addresses. And these are actually changing a little bit. We're going to talk about that here in just a second. And I will see if I can pull up an example of this. Yeah, because it doesn't talk about IPv6. So we're talking about IP addresses. So there are 4 different octets. Each can go up to, from 0 to 255. There are a few private IP ranges. I wonder if so yeah, this is one of them, is the 192.168. And then you have 2 other octets that you can play with to build out that private network. The 10, I believe it's just 10 go. That should be, where the first octet is 10, I believe that is its own private network. And then 172. So here we have, these are the different IP ranges. So we already talked about 192.168, 10.0.0.0 to whatever, you get those last 3 octets. And then we got 172.116. And then you can do 172.131, that gives you a couple octets to play with as well. A little bit more than that, but you get it. And here, this actually shows you how many IP addresses you can play with each IP address range. The 10, as you can tell, the 10.x gives you way more IP addresses, over 16 million. I mean, almost 17 million IP addresses. And so that's, if you're wanting to build a huge private network, using the 10 IP range is pretty good. So you're probably already familiar with IPv4. That's really what we've been playing with. That's where you have those 4 different octets. However, a problem kind of started to appear where you have a growing proliferation of devices on the internet, but you only have so many IPs that you can really play with, right? And so you need a new method for creating IP addresses to continue to assign to new devices that, basically ups the limit of the amount of devices that you can have on the internet. And so we're going to talk about this picture right over here on the side. This is from Comparitech. So credit to them for this graphic. So here on the right side, you can see IPv4. And you see kind of what that looks like. Again, it looks a lot like what we were talking about. And the range is 4.3 billion possible addresses. Now that might sound like a lot, but there's 7 billion or over 7 billion people on the planet. Does everybody have a device? I mean, that's a great question. I'm not exactly sure, but most of them probably have some kind of a cell phone, some sort of a mobile device, which might require, it probably requires an IP address. Then you have all kinds of other devices that businesses have that need to be public facing. And so that number is really very small. IPv6 on the other hand, and you see the kind of the schema for these addresses, it definitely looks a little funky. And it's using hex or hexadecimal to kind of express the address, but it gives you 340 undecillion possible addresses, and I've literally never heard of that number before. So let me real quick pull up a tab on how many zeros undecillion is. Undecillion has 36 zeros. So that's a lot of IP addresses, right? It gives you, as you can imagine, a much wider flexibility on devices that you can be putting onto the internet. So we're actually, no, I lied. They do have it here. I'm a goof. I didn't even see this graphic. So you do see IPv6 here, talked about here. And, they're kind of going through really the backstory of what's going on. So yeah, they talked about it. 340 trillion plus. I mean, unbelievable. A lot of IP space. And you can see this is really like what a full IPv6 address will look like. I mean, as you can imagine, the amount of variance here is, 340 trillion plus, right? So that's not the only unique identifier that devices have. They also have a MAC address. And this is what a MAC address looks like. And these can be assigned to actually like the physical device. And these are also expressed in hexadecimal. So you get a lot of obviously uniqueness in these kinds of addresses. So it's split. The first three sections are who built the network interface. And then on the right three, you have the unique address for the network interface. So there is a schema to it. They can be faked or spoofed. Like we already know that IP addresses obviously can be faked or spoofed. MAC addresses can also be faked or spoofed. And this happens, whenever it's basically pretending to use another. I mean, by definition, what spoofing is. So, be careful. What does IP address stand for? Internet Protocol. That's what I thought. Whatever. What each section? Octet. And how many sections and digits do they have? How many sections? 4. Was a MAC media, right? Media access control. Yep. Okay, so let's go ahead and deploy the interactive lab, and let's look through that. Beautiful. So Alice is sending packets through the router to tryhackme.com. Okay, so let's try requesting the site. Bob starts doing the same thing. So Bob's requests are being routed to trash. Why is this? Bob's. Okay, so that must mean that there's some sort of a block on his MAC address. So let's try spoofing Alice's MAC address. 32F 3339. Let's try requesting again, and the requests start going through. So, sometimes you might have some sort of a block going on, and to get by that, if you are spoofing, that might get you past a block. Because again, the router in this case believes that you are Alice. You are not Alice, but the requesting MAC address reflects that of Alice, so it's going to treat you like Alice. That's why it passes it on to tryhackme.com. So ping, and you probably know what ping is, but if you don't, super cool, you're in the right place. It is one of the most fundamental tools available. It literally lets you check if a device is up, like available to the internet and responsive, or if it's down or not responsive. And it will show you it'll show you how many packets it receives, how many are lost, and how much time it actually takes to respond to that. So what protocol does ping use? ICMP, which ICMP stands for Internet Control Message Protocol. Super easy, super simple. You've probably, again, played with ping, and that's a great way to test if you have connectivity to the internet and you're not sure. Literally ping Google 8.8.8.8, and if it's responding to you, then you are connected to the internet. So good to go. So go ping 10.10.10.10, and then let's go ahead and check the interactive side. It's probably going to say ping blah, 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 blah. So let's go ping 8.8.8.8, and it's literally, so this is just going to send I believe 4 packets to 8.8.8.8 to Google. 4, yep, there you go. And it'll return a flag for you. So super easy. Ping is very fundamental. You've probably, if you are further along in your cybersecurity journey, you've definitely played with ping at some point. If you've messed around with networking, you've played with ping before probably. But if you haven't, you're in the right place. That is exactly why we're here. So the next thing we're going to look at is the LAN room. So the intro to LAN includes 5 different tasks. We're going to learn all about subnetting, ARP, DHCP, and then the OSI model. And we already have actually a video on the OSI model, but it's always good to dive back in because we like review, because we're nerds and we like to learn things. Now, local area network topologies. Over the last 10 years, there's been an experimentation and implementation of various network designs. In reference to networking, when we refer to the term topology, we're actually referring to the designer look of a network at hand. Let's discuss the advantages and disadvantages of these topologies below. So we're actually going to go through, we got a few different topologies here, and each have advantages and disadvantages. The star topology, the main premise is that devices are individually connected via central networking device like a hub. You can see that right here, graphically represented. It's most commonly found because it is reliable and scalable. You can add, depending on, you can just, beef this up and then just keep adding more and more devices. as it, and they mention it here, as it scales, more maintenance is required. And this is kind of like their critical node. If this goes down, all the devices that require it for networking are also basically taken offline. And so this is a critical point of failure that you'll become intimately familiar with. Remember that availability is an entire, part of the CIA triad. So it's not just from a security perspective. It could be from a, disaster recovery perspective. You want to make sure that that is up 24/7, so these devices are good to go, but also that it is secure, which is going to be, it can be a challenge. Bus topology. It relies on a single connection, which is known as the backbone cable. You can see that right here, and each device is hooked up to that backbone cable in some sort of way. Because all the data is destined for each device travels along the same cable, it is very quickly prone to becoming slow, and bottlenecked if devices within the topology are simultaneously requesting data. Now, this can absolutely happen, and it also depends on the strength of this cable, and how much data that it can actually handle at any given time. That's where like a denial of service attack can really come in. You're just like flooding this cable with requests, and some of them are getting dropped or lost, or they're just not making it to these endpoints. There's also little redundancy in place in case of failure. So the disadvantage because of that is a single point of failure along this backbone cable. If the cable were to break, devices can no longer receive or transmit data along the bus. So not fantastic. Sometimes you might, see this, but there are disadvantages to it. And then you got the ring topology, also known as token topology, boasts some similarities. Devices such as computers are connected directly to each other to form a loop, meaning that there's little cabling required and less dependence on dedicated hardware, such as within the star topology. So basically, they all kind of form their own network by being directly physically networked to one another. This works by sending data across the loop until it reaches the destined device. There's one direction for the data to travel across this topology. It is fairly easy to troubleshoot if any faults arise. I mean, you'll know if one of these devices go down and requests are no longer being forwarded. So let's say this device goes down, requests will come along the ring to this device, but they're not going to get forwarded. So okay, well, that's what I need to troubleshoot. Less prone to bottlenecks because they're, kind of going around the whole ring, but it is a double-edged sword because it's not an efficient way of data traveling across the network. Again, like for this device to reach this device, it has to go all the way around. So that's kind of a pain in the butt. So what is a switch? A switch is a dedicated device within a network that is designed, whatever. It is designed to aggregate multiple other devices, such as computers, printers, or any other networking capable devices using Ethernet. These various devices plug into a switch's port. Switches are usually found in larger networks, such as businesses, schools, similar-sized networks, where there are many devices to connect to, or on the network. Switches can connect to a large number of devices by having ports of 4, 8, 16, 24, 32, and 64 for devices to plug into. So both switches and routers can be connected to one another. The ability to do this increases the redundancy and reliability, you can read it as, of a network by adding multiple paths for the data to take. If one path goes down, another can be used. Whilst this may reduce the overall performance of a network because packets have to take longer to travel, there is no downtime. A small price to pay for salvation. You're networking Thanos. Snap and the network is down. What is a router? A router's job to connect. It's a router's job to connect networks and pass data between them. It does this using routing, hence the name router. Mind-blowing. Routing is the label given to the process of data traveling across networks. Routing involves creating a path between networks so that this data can be successfully delivered. So, pretty easy. Note that routers and switches are not the same. They are not the same. And I believe we'll back up and we'll look at that through the OSI model because there can be some some details with the OSI model about switches too. So a little thing to surprise, or a little thing to be excited about. So LAN stands for local area network. Routing, that's a verb given for routers to perform. I know. What device is used to centrally connect multiple devices? Switch. Okay, yeah. What topology is cost efficient to set up? Who's the bus, right? Because it's literally bus topology, and it's cost efficient because you have like that central node or that central line, and you just need to hook it up to the line. Is expensive to set up and maintain. Star topology. All right, now let's go ahead and check this lab out. This lab will take you through the flaws of different network topologies. In a ring, all devices are connected to, and this is actually, we've talked about this, but this will graphically represent it like I mentioned. So device goes down, cable goes down. Cable. Okay, so let's go and cut it. So as you can see, requests are basically stuck at that machine. Nothing flows anymore. Bus topology, all devices are connected to the single backbone. So there you go. Now it's kind of saying that, again, you can flood this and cause some of those requests to get dropped. So let's go 5. And let's just flood it, right? We're just gonna spam it and cause it to crash. See? We are agents of chaos. All right, so then for a star topology, all the devices are connected to a central switch, and every packet is sent to the device that it needs to go. So this is doing a lot of work, but again, let's say, we're an agent of chaos and I just want to hammer that thing. Now the whole network is gone. So each one of these has their pros and cons. We mentioned that the star topology, although it is the most expensive, it's the most scalable. So if you can really, harden this device, and this is what most orgs will do, is they'll just harden the crap out of this device and secure it, then, you'll be pretty fine on, the network availability. But if anything were to happen to that central node, you're gonna have some issues. So let's talk about subnetting. Who doesn't love subnetting? Let me take a drink. So as you're kind of building this out, you're creating your own network, right? But you're going to want to go ahead and split these networks into logical segments. So like, let's say you have an accounting network, you have an HR network, you have a finance network, you might have an IT network, you might have a security team, you might have a lab, so you want to have all these logically segmented, not only just so it's, less congested traffic wise, but also, so, let's say an attacker, breaches someone in accounting, they're not able to access someone in finance without going through this switch, where let's say, you beef up a lot of the security at this node, you'll be able to catch that kind of movement and lock it down. So all students send information in real life to the correct department. Networks need to know as well. And this is really where you're going to specify by subnetting. As we recall, an IP address is made up of 4 octets. We did that in the previous room. So if you haven't checked out the networking fundamentals or the what is networking room, definitely check that out, because we do break these down, as well as IPv6 and MAC addresses. So basically they will use the IP address to be able to identify where to go. But these octets will actually identify a network. So you can do, like, let's say 192.168.1, and then the range under 1 is like your accounting, and then 168.2 can be your finance network, and then all those 255 devices are in accounting, or your finance network, blah blah blah. You continue to do that, and then that way packets are routed to the right area and they're not getting sent to the wrong network. So subnetting provides a range of benefits, including efficiency, security, and full control. Absolutely. So what is the technical term for dividing a network into smaller pieces? Subnetting. How many bits are in a subnet mask? What is the range of a section octet of a subnet mask? So let's go 12255. There you go, 0 to 255. What address is used to identify the start of a network? What address? The broadcast? No. Default gateway. That's it. Default gateway. Well, let's talk about the default. No, let's review that because I got that wrong. Oopsie. It says right here, I'm an idiot. Network address. The address identifies the start of the actual network and is used to identify the network's existence. For example, a device with the IP address range of 192.168.1.100 will be on the network identified by 10. So yeah, that kind of makes sense. So it's basically just the start of the network. Goof address. Yep. What address is used to identify devices within the network? Host address. And you can see that here. This obviously can change. Doesn't have to be 100. It really is just whatever is assigned. And what is the name used to identify a device responsible for sending data to the entire network? Default gateway. And you might recognize these as, well, no, I lied. 255 would be your broadcast address, and that kind of like fires stuff off to the entire thing. But anyway, our protocol. Recalling from our previous task, the device has two identifiers, a MAC address and an IP address. Again, check out the What is Networking video. The ARP protocol, or address resolution protocol for short, is the technology that is responsible for allowing devices to identify themselves on a network. Simply, the ARP protocol allows a device to associate its MAC address with an IP address on the network. Each device on the network will keep a log of the MAC address associated with other devices. How does ARP work? Well, you get a request and you get a reply. So pretty simple, right? So when the ARP request is sent, a message is broadcast to every other device found on a network by the device, asking whether or not the device's MAC address matches the requested IP address. If basically like, hey, does this match? And then you'll get a response saying, yeah, I actually have it as this. If the device does not have the requested IP address, an ARP reply is returned to the initial device to acknowledge this. The initial device will now remember this and store it within its cache in ARP. So address resolution protocol. What category of ARP packet asks a device whether or not it has a specific IP address? ARP something? It was a request. I have like goldfish brain sometimes. Nope. What category of request? Okay. What address is used as a physical identifier for a device on a network? MAC address. And again, if that doesn't make sense, check out the What is Networking video. We talked about that there. What address is used as a logical identifier for a device on a network? IP address. DHCP. So this is the dynamic host configuration protocol. This is basically how, so let me just read this blurb. It would make more sense that way. IP addresses can be assigned either manually by entering them physically onto the device, or automatically and most commonly by using a DHCP, and that's dynamic host configuration protocol server. When a device connects to a network, if it has not already been manually assigned an IP address, it sends out a request, a DHCP discover, to see if any DHCP servers are on the network. The DHCP server then replies back with an IP address and device could use an IP address the device could use. The device then sends a reply confirming it wants the offered IP address. And then lastly, the DHCP server sends a reply acknowledging this and acknowledging that this has been completed, and then the device can start using the IP address. So this is literally, you have just joined the network. Hey, it's like, a player joins a football team. Hey, we're going to have you play with this number. Okay, fine. I'll play with that number. That's great. Good to go. So, hey, I'm new here. Can anyone give me an IP address? This is a really good graphic. Hey, sure. Here's the IP address for you. Yeah, perfect. That works for me. I'll start using that. All right, great. See you around. All right. So what type of DHCP packet is used for a device to retrieve? That would be the discover. DHCP type of DHCP packet does a device send once has been offered an IP address? That's going to be the offer. Ooh, nope. Big oof. Send once has been offered. Oh, that's going to be the request. See, I'm reading this a little too fast. Finally, what is the last DHCP packet to be sent? That's the ACK, short for acknowledge. So that is the LAN room. And the next thing that we're going to be doing is the Next will be the OSI model. And what is the OSI model? It stands for Open Systems Interconnection Model. And this text actually here on TryHackMe goes through everything really that you need to know about the OSI model. And it also lists it in order from application all the way down to physical. But we're going to go ahead and read that right now. There are 7 layers in order from 7 down to 1 is application, presentation, session, transport, network, data link, and physical. And we're going to go through every single layer here in this section. So the answers here, we go with open systems interconnection. There are 7 layers, and the term for whenever information gets added to data is encapsulation. And we will actually be hearing this term quite a bit, especially whenever you get into networking and how data gets added on and how things, how packets get put together. Encapsulation is a term and a practice to kind of get familiar with here. Let's jump to layer 7, application. You should be pretty familiar with the application layer of the OSI model because that's the layer that you interface with the most. Even if you're not in tech or you work in cybersecurity, the end user interacts with this layer the most. Anything with a GUI is operating at the application layer. So of course the answers here are pretty elementary, so you shouldn't really have a hard time putting these in. The answers are also in the text above. The next layer, layer 6, presentation. As the text here says, this is when the standardization starts to take place. At this layer, data is translated to a presentable and consumable form for human people. And so that's actually where we get the answer to the second question on this section. The presentation layer acts as a translator. It also notes that security features such as data encryption, think of HTTPS being the more secure and encrypted form of HTTP, that occurs at this layer. Let's jump 1 layer down to layer 5, session. This occurs whenever 2 computers or machines on the internet or any kind of network are able to establish a connection. You establish a session, and within a session, those machines transfer packets between one another, and that is how they communicate with one another. We're going to talk a little bit more about packets here in a moment, but that is basically just a chunk of data between 2 systems that is transferred within a session. We'll go an extra layer down to layer 4, transport. And this is kind of where things start to get pretty interesting. We're introduced to TCP and UDP. And this is actually something that we're going to talk about later on in this walkthrough session. We're going to talk about this later on because there's actually an entire room dedicated to TCP and UDP. But at this moment right now, let's be familiar with what TCP and UDP are. TCP stands for Transmission Control Protocol, and UDP stands for User Datagram Protocol. And these are 2 methods that data is transferred between 2 systems over the course of a session. Now, there are 2 different kinds of methods because TCP is more secure and better for downloading and, kind of better communications and stuff like that. It's way more reliable, and we'll talk about why that is in the next video. But UDP is kind of like it's a one direction thing. Computer A is sending data to computer B, and it doesn't stop to confirm whether or not that data actually arrived to computer B. It just continues to send data. So we have a couple graphics here on this walkthrough, and we see basically the packets are different segments of a specific file. So in this case, the file would be a picture of this adorable puppy, and it is broken into 3 packets, basically containing different segments of the final product, right? And so over TCP, the web server is going to confirm with the computer that it received each packet, so that way the final product is complete. However, with UDP, the web server doesn't care. It is just going to spit out those packets, and hopefully those packets will arrive. Well, as you can see in this example, packet 2 unfortunately was dropped en route, and so the final product was this sad, derpy looking puppy. Still adorable, still fuzzy, but very much incomplete. So running through some of these answers, we'll see that UDP simply doesn't care if data is received. And so TCP would be used for something like an email client, because obviously you want to make sure that the email makes it to the recipient. However, for something like video streaming, like you watching this right now, it doesn't, this is actually happening over UDP. It's not that YouTube doesn't really care that chunks of this video might get dropped en route to your device. It's that it needs to be able to send this information fast enough that you can actually receive this video in a high enough video quality. If it's getting to a point where some of those packets are getting dropped, then it'll actually lower the video quality. That's why sometimes you might be watching a video in HD and then it might drop to like 720p. That's because some of the packets it might be noticing is getting lost. And so it will lower the actual size of the packet so that way it can continue to do that. But say you were to download this video, you need a completed video to be downloaded. That would happen over TCP because obviously YouTube wants to make sure that the video you are downloaded is complete and whole and is of the quality that you would like. Now let's jump down to layer 3. All of this happens in a network. We do assume. And this is the layer in which you find IP addresses. And each computer might have a different preference on how they reach each other. Some computers might preference a shorter path and some might prefer a more reliable path. And those may not always be the same. But ultimately, they will find each other using an IP address. Jumping down to layer 2, we get to data link. And this is actually where we come up with MAC addresses. Every single device has a MAC address. Unlike the IP address, the MAC address cannot be changed. It is burnt into the networking card of your device. So I hope you like it. There's no removing it. It is with you. And now finally, layer 1, physical. And we are introduced to Ethernet cords. And this is actually something that you might be familiar with. You might have one plugged into your computer right now. But this is like the physical connection. So think of fiber optic cables and things like that. The physical method or the physical medium in which data is transferred. Now, at the end of the walkthrough, you get to play through a game and you get a cool little flag. And basically, to win the game, you have to guess the correct order of the OSI model. It's not too hard, but the flag, I'll let you get for yourselves. So in the last video, we were going through the OSI model, and we were actually introduced to packets using this graphic that we're looking at right now with the cute puppy. The final file is the full picture of this adorable puppy. However, it was divided in transport into little packets, and each packet, as you can see, covered a segment of that picture. There's a table here I think that is important to zero in on, especially while you're doing this walkthrough. It includes a header and a description of the header that you will find on packets. Here you have time to live, which sets an expiry timer for the packet in case it doesn't make it to the destination. It includes a checksum, which provides a level of integrity for the packet. It also includes a source address, so that way the destination knows where this packet is coming from. And it also includes a destination address, so that way it knows where it's going to. Now, a difference between packets and frames. A packet contains IP address sourcing information, so it knows the destination and it knows its source. A frame, however, doesn't have that information. In the last video, we were also introduced to TCP and UDP, and as a quick review, TCP stands for Transmission Control Protocol, and UDP stands for User Datagram Protocol. So we've talked a little bit about what TCP is, but how exactly does it work? Well, TCP is a protocol that you would want to use. It basically ensures that data will make it to its host. This, however, does make the flow of information slightly slower because with every packet being sent, there is a confirmation that it has been received. One thing that you should be familiar with, though, of course, to be able to catch whenever this is happening live on your network whenever you're running something called Wireshark or like Wireshark is the Tcp Three-Way Handshake. This is basically how two machines are able to initiate a conversation between one another. And we see here we have the graphic that shows the TCP handshake between Alice and Bob. Alice initiates the conversation by saying SYN or by sending a SYN packet. And then Bob responds by saying SYN ACK, basically acknowledging the SYN packet that Alice sent. And then Alice acknowledges that and fires an ACK packet back. So altogether, we have three different things that occur. It is a three-way handshake. After that, they're able to share whatever data they need to, and then have the conversation that they need to have, and then they close that conversation. That conversation is closed whenever Alice or Bob sends a FIN packet, and then Bob acknowledges the FIN packet and then sends a separate FIN response, and then Alice acknowledges Bob's FIN. And then at that point, the conversation is over. Pretty simple, right? Well, you can actually practice this in TryHackMe. This includes a flag, and I'll let you go ahead and find it for yourself. But now let's go on to User Datagram Protocol, or UDP. Unlike TCP, UDP doesn't care. UDP lives its life. UDP sends all kinds of information regardless of whether or not it is received. A term to keep note of is stateful and stateless. TCP is stateful because it maintains the integrity of the session and it tracks that everything is being received. UDP, however, is stateless. It doesn't track that. It literally just spurts out information. Because it just kind of sends information, it's much faster. However, that might lead to unreliable data data reception. In this graphic, you can see that Bob sends a request to Alice for information, and then Alice sends the response directly to Bob. Alice doesn't exactly check to see that Bob received any of those responses. They're just gonna be there. To wrap up this room, we are introduced to ports. Now, what exactly are ports? We know IP addresses from the last room in the networking layer. And basically, an IP address is a unique networking address that each computer has. The device that you're watching this video on right now has an IP address. But how exactly does your device know which data is supposed to go where, which program it's supposed to be received from, what kind of data it's being received? After all, it doesn't just open up a giant collection bucket and just received all data as one, kind of thing. It actually organizes the data by what's called ports. And there are actually very common ports, and there's a table here showing some of those right now. For instance, there are 65,535 ports on your device right now. Not all of those are open, but there are several common ones that you should be aware of. For instance, port 21 is for file transfer protocol, commonly used to share files between two devices. Port 22 is a common one that you might already be familiar with, and that's for secure shells. Port 80 and port 443, that's actually how you browse the internet. Hopefully you're not using port 80 so much because that is the unencrypted, that is just HTTP. HTTPS, however, is done on port 443, and that is more secure. You're probably watching this over port 443. There are several other ports that you should be aware of, but port 80 and port 443, if you're just kind of like, if you're the end user, those are probably the most common ports that you use on your device. There is a practical on here that also includes another flag. I'll let you catch that as well. Now, first, we're going to talk about the introduction to port forwarding. This is an essential component to being able to move data securely from an internal network to the internet. Now, before we get too into the weeds here, we need to be familiar with something. We already know about IP addresses. We talked about that in the Osi Model video, and we already talked about in the last video talking about packets and frames and that kind of thing. However, there are specific ranges of IP addresses that are known as private IP addresses. For instance, 192.168 is known as a private IP address range. And that basically allows for you to create a large and scalable internal home network. You can literally have anything from like 5 devices on your internal home network to thousands of devices on your internal home network, depending on how you network it. However, those devices likely need to communicate to the internet somehow. After all, you're watching this video, right? And unless you're watching this from YouTube corporate, in which case, howdy, how's it going? Great to meet you. Then you're definitely not able to get this video feed from your internal network. And that is how port forwarding enters into the conversation. Your router has an internal and an external IP address. And the internal IP address will be a private IP address, like a 192.168 kind of IP. And then its external IP address will be unique to it, and it'll let the internet know what address to be able to route the request from your device back to you. But we also talked about ports, and say you're watching this on port 80 because you enjoy having no encryption. You live wild. Then you will send that request to port 80 of your router, but it will also translate that to port 80 for the external side, and then it will forward it off to the internet. You can configure this, so say you don't want port 80 open to the internet because everybody in the world knows that port 80 is unencrypted HTTP, and they want access to that. So say to add a little bit of ambiguity to the ports, you want to use, say, port, 33333. You can open up port 33333 on your router and then say, okay, whenever I send a request to port 80 on the internal side of your router, I want you to send that through port 33333 on the external side. That's how you can do port forwarding. Now, that doesn't necessarily mean you're like 100% secure. If an attacker scans your device and they scan all the ports and they see that port 80 is closed, but they see that HTTP is still open on port 33333, well, then they still see it. However, if they're not scanning for all ports, they're only scanning for the well-known ports, and they see that port 80 is not open, then maybe they'll move on. But there's a number of other functions that port forwarding is totally good for, so definitely look into that if that's something you're interested in. Next, let's talk about firewalls. This is very important. A firewall is basically responsible for protecting your network, and you can set up a number of rules with a firewall. For instance, if there is a known hostile IP address on the internet that you're familiar with, you can tell the firewall to drop all packets coming into your network from that IP address. It will also inspect the packet and look for signatures of maliciousness. Now, a very important fact to know about firewalls is there are two kinds. There are stateful and there are stateless firewalls. A stateful firewall looks at all packets and the context between them, but a stateless firewall only looks at each individual packet. There's all kinds of information to be gained in either case. An individual packet in and of itself might contain an amount of maliciousness. However, one packet on its own may not be malicious. However, a number of packets put together might be malicious. So there's definitely pros and cons in either case. These also operate at different levels of the OSI model, layer 3 and layer 4. This practical includes a flag, so I'll let you work through it, but this is a great visual representation of how creating a firewall rule can stop, in this case, a denial of service attack, where an attacker is trying to overwhelm an internal server with tons of pointless requests. Now let's talk about virtual private networks. This is another thing that we've talked about on this channel long ago. You can check that out if that's something that's interesting to you. However, let's talk about it right now as well. Say you have two networks and you're in network A and you want to get access to network B. We'll say network B is a business and network A is your home. You can use a VPN to be able to authenticate into network B over the internet in a secure tunnel, and that will allow you access to internal resources on network B. This is a technology that has allowed for work from home. So all through the pandemic, people were able to utilize VPNs to be able to get the job done. This is also something that people use to be able to access systems in other countries, and that allows them to have a layer of anonymity with their network traffic. It's not perfect, but it definitely can help. Say you're in a country like China and you don't have access to a resource like Twitter or YouTube, and you wouldn't be able to watch this video, which makes me very sad. You can use a VPN and access YouTube and then watch this video, and we can be friends. 大家好，我是 StudioSec. So here we're introduced to three different VPN technologies: PPP, PPTP, and IPsec. I'll let you go through this table and take some time to study it, but it's definitely something that is important to know later on. Now let's talk about LANs, and this is actually something that we've talked a lot about already in a previous walkthrough from this actual series, and you can check that out. But here's kind of a nice little refresher. We're talking about routers and switches and how switches can provide some scalability on your network. An important thing to note is that there are two different kinds of switches. One switch can operate at layer 2 while another can operate at layer 3. Layer 2 switches will forward frames, but layer 3 switches will do that and they will use IP addresses, meaning that a layer 3 switch can actually really help scale up your network. As you can see on this graphic, this switch is actually creating two separate internal virtual local area networks: 196.168.1.1 and then 192.168.2.1. These are two separate internal networks that this switch is able to route between. Now, although I use that term route, it is not a router, so definitely do not get a switch and a router confused. Now, to wrap this room up, we have another practical exercise that you can check out. Again, another flag. I'll let you go ahead and do this on your own, so that way you get the practice. So that has been the networking fundamentals room in the intro to cybersecurity room on TryHackMe. The next thing that we're going to be doing is the DNS in detail, and if that is already out when you're watching this, that will be the top video. If it's not out yet, then definitely hit this bottom playlist to see what other walkthroughs in the series we've already published. With that, I'll see you all next time.